Morning. Can everyone hear me? Okay, so last class we ended at compound proposition, and I asked you to you can make your own compound proposition and then trying to construct the truth table for it. So today we will look at the propositional equivalence. It's like if we have a multiple compound proposition, how do we know they are talking about the same thing? Okay, so before we going on to the propositional equivalence, there is two terms you need to know. Is first is well, a compound proposition is always true, no matter what's the choose value of your propositional variable, then it will be then this kind of compound proposition will be called tautologed. Like if a compound proposition that's always false, no matter what the propositional variable, then we call it contradiction. Now, if a proposition that's not a tautology nor a not a contradiction, then we call it contingency. Okay, so let's look at an example. So let's say we have a propositional variable, p. Now the choose value for p, it could be true or it could be false. Now if we want to negate the p, we will have when p is true, then not p will be false. When p is false, then not p will be true. Then if we apply the disjunction on p or not p, then we will get both true value, right? Since for disjunction, it's only false when both your propositional variable is false. But you don't have them to be both false, so it will be true. And when you apply the conjunction on p and not p, conjunction is only true when both of your variable are true, but you don't have them to be both true, so you will get both false for p and not p. So if you look at this compound proposition, the truth value is always true. So this will be an example of tautologed, where p conjunction with not p, since they are both false, this will be a contradiction. Any questions here? Okay. Now we will look at definition of logical equivalent. So the compound proposition P and Q are called logically equivalent if and only if Q is a tautologist, which means if you construct a truth table for P if and only if Q, then all the truth value for P if and only if Q will be true. Then in that case, we will denote P, and you see the 3-line Q. So this notation, it's what we call the equivalent. So we will read that P equivalent to Q. And this denotes that P and Q are logically equivalent. Now, if you look at when does the P if and only if Q is tautologist. If P if and only if Q is tautologist, that means all its truth value need to be true. And we know if and only if statement is true when both of your variable are the same, right? So either they are both true or both false. So that means P and Q must be either both true or both false. Right? So whatever the truth value you have for P, it must be the same for Q in order to make the if and only if statement all true. So in other words, compound propositions that have the same truth value in all possible cases are logically equivalent. So if you see two compound propositions, their truth value on the truth table are the same, then you know these two compound propositions are equivalent. Any questions? So we can look at an example. So let's say we want to show that not P or Q and not P and not Q are logically equivalent. So that means we need to show either they have the same truth table or not P or Q if and only if not P and not Q will be a tautologist. So let's construct a truth table. So we have two variables P and Q. And there are 4 possible outcomes. You can have both true, true, false, false, true, false, false. Now we need to construct not P or Q. So before we construct not P or Q, we have the parentheses around P or Q. So we will do that first, P or Q. And we know P or Q is only false when both values are false. And then we will negate it. You'll have false, 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 true. Then we finish this one. Then we need to construct not P. So not P will be false, false, true, true, and not Q will be false, true, false, true. Now you will apply the conjunction. And we know conjunction is only true when both of your variables true. otherwise it will be false. So now we finished constructing the truth table for both compound propositions, so we'll compare it. So if you look at their truth table, so we see that they have the same truth value. And since they have the same truth value, they are equivalent to each other. Right? Or by the definition, not P or Q, if and only if not P and not Q. So if you compare it, if and only if statement is true when they are both true or both false. So you have them both false is true, both false, and both true. So either way, you show that these two compound propositions are equivalent. So you can conclude that not P or Q is the same or is equivalent to not P and not Q. Any questions here? Okay, so let's look at another example here. We want to show that P implies Q and not P or Q are logically equivalent. And this one has a special name. This is known as the conditional disjunction equivalence. So again, to show they are logically equivalent, we can show P. We have two variables here, P and Q. And for two variables, we have four possible outcomes: true, 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 false, false, true, false, false. Now we need to construct P implies Q. And we know implication is only false if your hypothesis is true but your conclusion is false. So when you have a true false, otherwise it will be true. Then we need to construct not P or Q. So we need to construct not P. So not P will be false, false, true, true. And then we will have not P or Q. And we know the disjunction is only false when both of your variables are false. Otherwise, it's always true. So you have false, then true, true, true. Now, if you compare P implies Q, if and only if not P or Q, If you compare their truth table, they are the same. True. You have they are both false, both true, both true. Right, so if you look at their truth value, they are the same. So P implies Q is the same as, say, not P or Q. Any questions here? Is everyone here? And now if you look at this example, how many propositional variable do you see here? So for this question, you want to show P or Q and R, and P or Q and P or R are logically equivalent. So this is the distributive law of disjunction over conjunction. So how many propositional variable do you see in this compound proposition? Anyone? Okay, so we see three, right? We see P, Q, and R. Now for P, Q, and R, how many possible combination are there for the truth table? Or in other words, how many rows do I need to construct here? When we have only P and Q, there are 4 rows. Now we have 3 variables. How many rows need to be there? Okay, so I see people say 8. So if you look at it, if we only have 2 variables, so let's say we only have Q and R, we can have true, 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 false, false, true, false, false, right? So there are 4 ways just for the 2 variable. Now, if I have one extra, I will have one more variable, right? It could be either true for all the 4 possible combination, or it could be false. So there are 8 possible combination out there. Now, if you have 4 propositional variable, how many rows do you need to construct? Then it will be 16, right? So pretty much what you do here, you will make a copy of it, and then for the 4th variable, it could be all true or all false. So half of it for the new variable will be true, half of it for the variable will be false. So now let's construct this compound proposition. So we first need to have Q and R. And again, the conjunction is only true when both of your variables are true. So here will be true, here will be true. The rest, it will be all false. Because here it is both true and both true. All other places, you have at least one F. Then we will construct the P or Q and R. Now we will apply the disjunction to P. And we know disjunction is only false when both of your variables are false. So if you look at it, you have false, and they are all false. Besides that, you have at least one true. So the last 3 will be false. The remaining will be all true. Now, if you look at the next one, we need to construct P or Q. And also we will construct P or R. So disjunction is only false when both of your variables are false. So if you look at it, if you look at the P and Q column, look for when they are both false. Here, the last 2. And for P and R, again, we look for them to be both false. So the last one and the second to last one. All other places will be true. And then we can apply the conjunction on the 2 propositions. And for conjunction, it's only true when they are both true. So you have true, 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 and then you have false, false, false. So we finished constructing the truth table for both compound proposition. Now, if you take a look up here, so if you compare the truth value here, they are the same. We have 5 true, and then the last 3 is false. So that will show they are logical equivalent. Any questions here? Okay, so this is the truth table we just construct. So let's look at some logical equivalent that have a name to it. So if you take P, do a conjunction with a tautologed proposition, which means a statement or proposition that's always true, then this compound proposition will just equivalent to P. Right? Because when we apply the conjunction is only true when both of your variable is true. So if you already know one of the variable is true, or one of the compound propositional value, right, it's always true, then the result of P and a tautologed will be depends on your proposition P. Because if P is false, then you have a false value conjunction with a true value, and then for conjunction, it's only true when both of your proposition is true. So if one thing is false, it will be false. Now, if P is true, then you have them both to be true, then this compound proposition will be true. So whatever P and a tautologed, the result depends on the P. So this is just equivalent to P. Now with the disjunction, the OR relation, it's only false when both of your statement is false. So if P is true, it will make this compound proposition true. If P is false, you have both false, it will make this compound proposition false. So P or a contradiction proposition, the result is depends on the truth value of P. So P or a conditional proposition, it will just congruent to P. So that's the identity law. Right? So when you do a conjunction with a tautologed, or when you do a disjunction with a contradiction, you will get whatever your original proposition back. Right? It's equivalent to just the original proposition. Now, if you have a P or right, do a disjunction in a true value, so we know for disjunction, it's only false if both of them are false. And since you have a tautologed, one of the propositions is always true, then it will make the statement true. So you don't really care about the P. Now, when you have P conjunction with a false statement, right, or a proposition that's always false, then your result will be false, because the only time to make a conditional statement, to make a conjunction statement true, is when both of the statements are true. So since one of them is false, then this conjunction will be false. So this will be a domination law, right? So on the disjunction, true, a tautologed statement, tautologed proposition will dominate this compound proposition. In the conjunction, the false statement will dominate the result. Now, when you have P conjunction with P, Q conjunction with P conjunction with P, P disjunction with P, it will just equivalent to P. But this is like you saying P and P or P or P. They are the same. You are talking about the proposition P. Now, when you negating a negation of P, so you have not P, it will just give you P back. So that's the double negation law. And when we have P or Q and Q or P, they are equivalent. So this is the commutative law. Right, so P or Q is the same as saying Q or P. Same thing with P and Q and P. The order doesn't matter. And the associative law also apply in the conjunction and disjunction. So when you have P or Q or R, you can do the P or Q first, or you can do the Q or R first. Same thing with the conjunction. For the P and Q and R, you can do the P and Q first, or you can do the Q or R first. Okay, and there are also the distribution law. Where someone have P or Q and R, that you can distribute this to each variable. So you can have P or Q and P or R, right? So you are able to distribute it. Now you can have the conjunction over the disjunction. So you have P and Q or P and R. Right, so that's the distribution law. And we show one of the truth table earlier. Right, so if you look at this one is what we showed earlier. Now you can try to construct the truth table for the second one. And now let's look at P or P and Q. You have P and P or Q. So if you have P or P and Q, then this is the same as just this is equivalent to P. But since you are saying P or P and Q, so in order for this to be true, you need to have both P and Q. But once you have the P, it satisfies the left condition. It satisfies this condition here. So P or P and Q is just congruent to P. Now if you have P and P or Q, this is same as saying the P. Right? Because in order for this to be true, P must be true. And P is true, you have P or Q. So P must be true here. Then if P is true, you don't need to care about whether you have Q or not, since this is disjunction. So this is the absorption rule. And the last one you will see is the negative law. It's when you have P or not P, this is always true. right? So this is the example with the example earlier I gave you for the tautology and the contradiction example. So have P or not P is always true, and have P or not P and not P is always false. So the first one is always true is because you can either have P or not P, right? Because P can either be true or false. So P or not P is always true. Where when you have P and not P, it will be always false because you cannot have a proposition that being true and false at the same time. Any questions here? Okay, so here are some logical occurrence that involving conditional statement, like P implies Q. So P implies Q is the same as saying not P or Q. So this is, I would say, an important one. You should memorize it or you should understand it. So this is saying that if you have P implies Q, this is the same as saying not P or not Q. So I'll give you an example. So earlier in the class, we let P to be pass 3 exams. Right? We say if you pass all 3 exams, you will pass a course. Now, this statement is the same as saying that either student don't pass. This is saying that student will either not pass the 3 exams or they pass a course. Because what are all the possibility here? Student pass all 3 exams, which means they pass a course. Or they don't pass 3 exams. And if they don't pass all 3 exams, then anything could happen. So this is saying that a student will either pass a course or they don't pass the 3 exams, right? So pass a course is the Q here, or they don't pass the 3 exams. So that's here. Any questions? Okay, so the next one, P implies Q is the same as not Q implies not P. So we shown this, I think previous class as well. And this one have a special name to it. Right, this is the contrapositive statement of this is the contrapositive statement of P implies Q. right? And then we know P implies Q is the same as saying the contrapositive statement of it. And we showed that before, right? So pass 3 exam, if you pass 3 exam, you will pass a course. This is same as saying, if a student don't pass a course, it will imply that the student must not pass all 3 exams. Okay, so here we have P or Q. This will be equivalent to not P implies Q. And P and Q will implies negation of P implies not Q. So this two you can derive it from the first one here and the rule we learned in previous slide. And to negate P and Q, this is same as saying P or not Q. And this is something we showed last class. How was negation of P implies Q. So this is also important. Right? Because the only time P implies Q is false is when you have P is true, but you have Q is false. So we have P and not Q. So that's the only time you will be made P implies Q false, which means this will be the same as negating P implies Q. Okay, next, you have if P implies Q and P also implies R, then you will be able to know P will imply both Q and R. Right, since you have and here, right? You say P will implies Q, P will also implies R, then P will imply both Q and R. Right, so normally people are okay with this one. Now here you have, if P is true, P will implies R. And if Q is true, Q will implies R. So both P and Q are able to imply R. So we know P or Q are implies R, right? Since both work. P is able to imply R, Q is able to imply R. So here is OR. So this N here, when you combine the two, it will turn out to be P or Q implies R. Right? Since both P and Q are able to imply R. Now here you have if P implies Q or P implies R. This means one of the two proposition could be true or both. You don't know. So you know P is able to imply Q or R. You don't know which one. It could be only one of them. It could be both. So you will keep this OR relation here. Now, if you have P implies R or Q implies R, so you know P is a either P is able to imply R or Q is able to imply R. Maybe both, but you don't know. So this means in order to imply R, you better to have all of them. If you have P and Q, then it must be able to imply R. It must be able to imply the R here. Since you know at least one of them will be able to imply R. So to guarantee that this will happen, you need to have P and Q. Any questions here? I see people asking, can you go over the third and then the fourth one again? Okay, so for the third and then the fourth one, it's really, you are able to derive it from the other one. So here you're saying that you have P or Q. So this is saying that not P implies Q. So if you just take this, so I can derive this from the first one. Right, so let's say you start from not P implies Q. From the first condition, what do you know? If you apply the first one, then you will have negation of the first proposition or the second condition. So you have negate here is your first proposition. So you will negate the first proposition or the second proposition. Now what's negation of P? That will just give you P or Q. Now to negate it, you have P and Q. So P and Q is the same as saying P implies not Q. So if P does not imply not Q, what will happen? Right, so for this one, you can derive this one from the negation of P implies Q. Again, if you start with the right hand side, implication of P, you want to negate P implies not Q. So P implies not Q. When you negate it, you will get what? You will get P and not Q. But you will get P and not Q. Because the only time the implication is false, it's when you have the assumption is true, right? So P is true, and you have your conclusion is false. So in here, your conclusion is not Q. So you will negate the not Q. And you have negation of Q, and that will just give you P and Q. So that's why I didn't really go over the third and then the fourth one, since the third and then the fourth one, you can derive it from the other one. Any questions here? The last one is this one. Okay. So I will say this one. So these two are easier to understand. Or because you have P implies Q, P implies R. Now, if you have a relation, that means P will implies Q, P also implies R, then P is able to imply both Q and R. If you have P implies Q or P implies R, you don't know which one will imply or both. So you know P will able to imply Q or R, right? So this notation here is the same. Now the confusing one, it will be the last one here and then the third to last one. So here we have P implies Q. So you have P implies Q. Wait, sorry. You have P implies R and Q implies R. Right, so this means P alone are able to imply R. Right, so you have the N relation here. Right, so you have P implies R and Q also implies R. So this is the same as saying P or Q are able to imply R. This is or because you don't need both of them to be true in order to imply R. as long as you have one of them, you are able to imply R, right? Since you say P is able to imply R and Q is able to imply R. So here we kind of turn this N to an OR here, right? Since P or Q both are able to imply R. So as long as you have P or Q or both, it's able to imply R. Now the last one here is saying that you have P implies R or Q implies R. So this or here will make you, so this or relation here, you can't guarantee that P implies R or Q implies R. So we know we don't have or relation, either the first proposition is true or the second one is true, or both, you don't know. So it's possible that only one of the two is true, right? Since you have or here, so you are saying either you can have P implies R or you can have Q implies R. You don't know which. So in order to guarantee that R is true, you need to have P, both P and Q to imply R is true. So this way, no matter you have P, no matter the first one is true or the second one is true or both one is true, you can always imply the R. So in order to do that, you need to have both P and Q to guarantee that happen. Do we see that? Okay, so I would say the important one will be the one I highlight. Okay, now let's look at some logical equivalences involving biconditional statement. Now for biconditional statement, right, we briefly talked about the last class. So we have P if and only if Q. This is the same as saying that P will imply Q, Q will also imply P. They imply each other. So here you have P implies Q and Q implies P. So you kind of break it, you will break this biconditional into two implications. So I think most people are okay with this one because this if and only if just follow with the definition. And this is actually how we're gonna do if and only if proof later, where you will need to do two implication. Now the next one you have P if and only if Q is the same as not P if and only if not Q. And we know for if and only if statement, they will either be both true or they will either be both false. So if P is true, it will imply Q is true, vice versa. So if P is false, so have negation of P, that will imply negation of Q as well, vice versa. Okay, so here where you have P if and only if Q, that means either you have P and Q, they are both true, or you have not P and not Q, they are both false. So these two are pretty much talking about the same thing. Now to negate P if and only if Q is the same as saying P if and only if not Q. So this is saying that P if and only if Q is false if P and Q don't have the same choose value, right? So if you see you have P if and only if not Q. So this is saying that when P is true, you want to negate the Q. When Q is false, you want to negate that you will be on Q is true. Any questions here? Okay. Now with the law here, for the last one. Okay, I see people asking for the For the last one, do we have to have exact opposite choose value for all cases? Yes. But here, to negate the P if and only if Q, the negation is to make all choose value. You will have all the choose value opposite. Now this is saying that by negating P if and only if Q, you will get P if and only if not Q. So I can show you. Let's have PQ. We have true, 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 false, false, true, false, false. And then you have P if and only if Q. And we know if and only if statement is only true when their truth value are the same. Now to negate it, you will get false, true, true, false. Now you need to do P if and only if not Q. So I will construct not Q. Not Q will give you false, true, false, true. And then you have P if and only if not Q. So you are comparing P and not Q. So it's only true when they are both true or both false. Okay, so the negation P if and only if Q, it will be opposite of here. So it will be false, true, true, false, false, true, true, false. Okay, and then here to have these two column, either they are both true and then both false. So the middle two is true. And then first and last one is false. Now if you compare it, they have the same truth value. Now, when you say do they need to have exact opposite truth value? That's when you're comparing P if and only if Q and P if and only if not Q. These two will have exactly opposite truth value, but by negating it, they will have the same one because this is the negation of P implies Q. Does that answer your question? So with the law I give you with the logical equivalences, you are able to show two compound propositions are equivalent without constructing the truth table. Now the reason is if you have just two propositional variables to construct a truth table is not too bad. So you only have 4 rows. But when you have more propositional variable, right? When you have 3 variable, or when you have like 4 propositional variable, then you need to construct 8 row, 16 row. Then constructing the truth table will be a lot. So if you look at here, we'll have not P. So we want to show not P implies Q. Now, how do we show this is true? Well, we know that P implies Q is equivalent to Q or not P. Or I can write it as not P or Q. Right, so this is the one I highlight and ask you to memorized. So here we will have not P or Q. Now to negate it, we will apply the De Morgan's law. Let me see here. Okay, so the De Morgan's law here is saying that when we negate the conjunction, not only you need to negate P and Q, it will also flip the conjunction to disjunction, and it will flip the conjunction to disjunction. So when you negate the conjunction, you need to negate both P and Q, and it will change the conjunction to disjunction. When you negate the disjunction, not only you negate the P and Q, you will also change the disjunction to conjunction. And I can give you example for De Morgan's law. The reason you need to negate the conjunction disjunction is, imagine you have like John is CS and math major, which means double major. Now, to contradict this statement, you only need to negate one of the major here. So as long as John is not CS major or John is not math major, it will be able to contradict that John is a double major in CS and math, right? So you don't need to negate both CS and math major to negate John is a double major. As long as John is not CS major or he's not a math major, it's able to contradict that John is both CS and math major. So that's when we negate that, you need to change the N to a or. Now again, if I change this to a or, if you have John is CS or math major, to contradict that statement, you need to say John is neither CS nor math major, right? It cannot be CS and math, right? Because here saying that John is CS or math major, which means it's okay that John is not a CS major. He might be the math major. And it's okay that John is a math major, but not, it's a CS major, but not a math major. The only way to contradict this statement is John is not a CS major and he's not a math major, neither. So if John is neither, there's two major, then you will contradict that John is CS or math. So since you need to have, you need him to not major in both CS and math major in order to contradict CS or math, or you need to have the and relation here to contradict the or relation here. Okay, so let's go back to our exercise. So now we want to negate the disjunction. So we'll negate each proposition have not P. We will negate the not P, and you will flip the disjunction to conjunction, and they have not Q. And you have negation of negation P, so double negation, this is P, and then you have not Q. So you're able to show negation P implies Q, it's congruent to P and not Q. Any questions? Okay. Now here we have negation of P or negation of P and Q. I want to show this is congruent to not P and not Q. Okay, so here we're trying to negate P or another proposition. So so here we will apply the De Morgan's law again. So we'll negate the P and then we'll flip the sign and then we'll negate not P or not P and Q. Okay, and now we will take care of this part, right? So another De Morgan's law. I have not P, and so we'll negate not P, and then we will flip the N to an OR. So we'll negate the Q. So have not P and, so here we have P or not Q. So what do we have here? We have the conjunction here and we have the disjunction here. So we can apply a distribution law. So we can have not P and P, or then we will distribute it to not Q. So we have not P and not Q. And here we have not P and P. So can we have not P and P? Okay, so if you'll say no, so this means it will always be false. Right, so not P and P will always be a false statement. So this is the contradiction. Or you have false statement or not P and not Q. And then we learned that when we have a contradiction or relation with another proposition, since this is all relation, it's false if all the proposition is false. So if this part is true, then it will make the statement true. So when you have all relation with a false statement, you can kind of ignore this or. The answer will depend on wherever the proposition have not found yet. So if this is true, it will still make this proposition true. If this is false, it will make it false. So you can ignore the or contradiction. So you will have not P and not Q. So now if you look at it, you are able to show these two are congruent to each other, are equivalent to each other. Any questions here? Okay, so let me show one more example. So on this question is asking to show this proposition is a tautology, which means we want to show this statement will end up to be always true. So we have P and Q implies P or Q. Now the first thing we should always do is to get rid of the implication. And we know P implies Q is congruent to not P or Q. So we can have not P and Q or P or Q. Now we will negate P and Q with not P or not Q. We have or P or Q. Now if you look at it, we have disjunction everywhere. We have or. Now if we have only the disjunction, that means we can apply the commutative law and the associative law. So you can do it any order you want. So I will do not P with the P, so I have not P, or we can do not Q or Q. So I will group the not P with the P together and not Q with the Q together. Now we have not P or P. This is always true. Right? Since P is either true or false, so one of it will be true. Or we have a not Q or Q. So we have a choose value or a choose value. Your proposition will always be true. So this shows that our statement will end up being a true statement no matter what's our choose value for the proposition P and Q. Questions here? Okay, if there's no other question, we will end today's class here. Just a reminder, next Monday through Wednesday, there is no class. So the next time we will meet will be the next Thursday, a week from today. Tuesday don't have class, Monday through Wednesday. So Monday, Tuesday, Wednesday, you don't have class. Right, so I think it's the, I believe it's the Labor Day and Rosh Hashanah. I see people say, once the next day we meet, it will be next Thursday. So a week from today. Okay, so I will see everyone next Thursday. Have a good weekend. A week from today will be on the 9th. So we'll have the class on the 9th.